What we call the power rule for logarithms comes directly from the idea that if we have some base b raised to a power m and then raise the whole thing to a power n, we get b raised to the m times n. Where if we have something like logarithm base b of m raised to a power p, because, ignoring that p for a second, log b of m is trying to identify the power of b that gets m, that's essentially this term in here. So, in the same way that we can pull in that as a multiple with our exponent, we treat this as a multiple for our exponent, which means we get a phrase that looks like plog b of m. It looks dumb, but the idea there is we're pulling down the outside exponent and treating it as a multiple. That's the traditional explanation for where the power rule comes from. Another way we can think about that is in terms of the rule we had that we talked about earlier, that if we take log base b of b raised to some power p, we can pull out the power p, because that's what it's identifying, the power of p there. Where we can also think of that as saying, okay, take out the power p, then we get log base b of b, which is just 1. So this is a general version of that rule for when we don't happen to have things fall into our nice patterns. So something like that logarithm of 4, the natural log of 4 in particular, we can say that that's 2 log 2, like I mentioned, for both the reason that I had there and the reason of the product rule. That is, the product rule, just like with regular arithmetic, is essentially just a shorthand for dealing with lots and lots of multiplications, because it's just the product rule pulled together a whole bunch of times to get powers. It's nothing too subtle, it just looks weird because we talk about plogs, I guess. But we should be careful here when we're talking about these things in terms of functions, in the same way you need to be careful about rational exponents and other places where the domain might change. That if we have something like the natural logarithm of x squared, that is the same as 2 times the natural logarithm of x, but only for x greater than 0, because natural log x isn't defined at negative places. But because of that square, the natural logarithm of x squared would be. So just be mindful of that when we're looking at things in terms of actual functions, that this is nice, but a thing we have to be very careful of. Anyway, let's get some examples here dealing with the more arithmetic side of things before we get to the equational stuff later. So for this example, we want to use the power rule to expand log base 6 of 2 raised to the power 7, the common logarithm of x minus 1 raised to the power 3, and the natural logarithm of the square root of 4x. So, again, lots and lots of practice here. For our first case there, it's pretty traditional. We have log base 6 of 2, it's a 6, not a b, raised to the 7. The power rule here says we just pull out that exponent, so we would get 7 log 6 of 2, or if we really wanted to think about what this looks like in terms of the product rule, we could understand that this is log base 6 of 2 times 2 times 2 times 2 times 2 times 2 times 2, 7 of them, which you could then split apart with 7 pieces of log base 6 times 2 to get 7 log 6 of 2. So again, like I said, the power rule is just a shorthand for the product rule because exponents are a shorthand for products, repeated ones that follow the same thing. So just a little bit more of an argument for why this works. Anyway, in that second case, if we have the common logarithm of the quantity x minus 1 cubed, we can just pull out that cube and get 3 log x minus 1. And then in our last case, we can be a little bit more subtle there, but we have the natural logarithm of root 4x. First, we can recognize that that is the natural logarithm of 4x to the 1/2, where again, we need to be very careful with these exponents as we go forward, that we're kind of saying this 1/2 is inside the logarithm. If it's on the outside, that's its own messy thing with compositions. We're not quite there yet. Don't worry about that. Here, we're saying this guy is on the inside, so we can pull him to the front, get 1/2 times the natural logarithm of 4x, and maybe we're happy with this as it is, but you know, we want to get more practice. I want you to get more practice, so I'm going to pull this apart even further and get 1/2 times the quantity natural logarithm of 4 plus natural logarithm of x. And I can pull this apart even further here, that is a 2 squared, just like we talked about before, which cancels with that 1/2. So we would have here the natural logarithm of 2 plus 1/2 of the natural logarithm of x. And as you're doing more and more of these things, that's the sort of special elimination. I don't know, it sounds weird when I say it that way, but that's the sort of thing you can be very careful of, that you don't lose track of those coefficients, you don't lose track of maybe positive and negative signs when you're dealing with quotients as well as products. There are a lot of subtleties there that go into this with how factoring runs together. Just take it slowly, especially as you're getting started here, and mind those sorts of details, because it's really easy to lose track of small things and get way off base, haha. Anyway, we'll next talk about how we can pull these things together to get some expanded terms as well as some condensed down terms.